Okay, so for this one, I'm going to help you find your zeros, which are always found by setting the denominator equal to 0. And in this case, we have a trinomial. So how do we solve trinomials? What's the first thing we do? Let's factor. So when you're factoring 6x squared plus 4x plus 2, is there anything special you notice? Yep, you have to take out that GCF. That's not only going to make it a lot easier for you to factor, but if you can't factor it, it's going to make it simpler to see whether or not you can factor. And I always like to double check it, so I do a quick distribution. 2 times 3, 6x squared. 2 times 2 is my 4x. 2 times 1 is my 2. And then I can set up my 2 brackets. I'm going to keep my 2 in front. So the only thing that multiplies to 3x squared is going to be 3x and x. Nothing else I can have. What's the only thing that's going to multiply to a positive 1 and make a positive inside? 1. So this is the only possible thing I could have. But if I check this, this is 1x plus 3x. Is that going to give me 2x? Nope. Okay, another way that you could solve a trinomial that is quadratic is by using what?
Quadratic formula.
Quadratic formula, great. So if you're using the quadratic formula, remember you have your a value, your b value, your c value. Okay, and then you would do x equals the opposite of b plus or minus the square root of b squared minus 4ac. Okay, now let's look and see what happens inside there. It would be over 2a. Okay, but let's see what happens inside the square root. You would get 4 minus 12. What's 4 minus 12? Minus what? Negative 8. What does that tell me about my solutions? They're imaginary. So, if there are no real solutions, there are no real zeros. Okay, so for that one, there are no real zeros. So we can't put them on the graph. Okay, no real zeros. Alright, so then from there, let's find our vertical asymptote, which is the 0 of the denominator. So if I set x plus 2 equal to 0 and solve, I get x is negative 2. That's going to be on my graph. And then for horizontal, that's when you compare the degrees. So you have to compare the degree of the numerator and the denominator. The degree of the numerator is what? 2. Degree of the denominator? 1. It's always the largest exponent. So the degree of the numerator is greater than the degree of the denominator, which means what in terms of the horizontal asymptote? There's none. Okay, so then of course you would ask yourself about the oblique. Is there an oblique one? Yes, we already talked about that. Okay, so yes, because the degree of the numerator is 1 more than the denominator. Okay, so it's exactly 1 more. So it can't just be greater, it has to be greater by exactly 1. If it was 2 more, there would not be an oblique asymptote. And then you're going to use long division to find it. So when you're doing long division, okay, this is something that we've done before, you start by dividing the first value by the first value. So what's 6x squared divided by x? 6x, right? So then you distribute. 6x times x is 6x squared. 6x times 2 is 12x. And then whenever you do long division, your next step is to subtract. So you have to distribute that negative, which will give you negative 8x. We're going to drop down the plus 2, and then the process starts all over again. So now, this is the first value. So negative 8x divided by x is what? Negative 8. When you multiply, these should always match exactly. And then you distribute. So this becomes plus, this becomes plus. So this is your remainder. Remember that your asymptote is always the quotient without your remainder. And so you have to put your y equals on it. Okay? And this is always linear. Okay, so this is your oblique. Okay, so now what we're going to do is we are going to put this in our graphing calculator and we are going to look at our table. I guess I can squeeze my table here or here, it doesn't matter. So remember, you want to see what happens on either side of that vertical asymptote, that -2. And when you're looking at that on your table, you know that's where the error occurs. Okay, now because I gave you like this little graph, we do have to think about the scale. When you're doing that on your own sheet of graph paper, you don't have to worry about that as much. But go ahead, put that in your graphing calculator. And then once you hit graph, when you're in your standard window, remember you have to ask yourself, is that the full graph? Yes or no? How do you know? How do you know? You should always have 2 branches, okay? Remember, we already know the shape of an oblique type of graph. We know it should look like this. We have these 2 like soft V shapes kind of slanted there. Okay, so when we're looking at this, we have to adjust the window. There are a few ways you can do it. Yesterday I showed you could go to zoom and do like zoom out. But the first time I zoomed out, that wasn't enough. So I have to press it again. And there it is. Okay, so I can see my X. That's really too wide, so I'm going to tighten up the window a little bit. Maybe I'll try -50 to 50 and see if that works. Okay, so that's good. I could go by 10s on my X's. I could do the same thing with my Y's. Let's see if I can even shorten up the Y's. Like maybe we'll do -60 to 60. Okay, and then so I can even go in even more on my X's. So let's try -10 to 10. Let's see if that part of the standard window works. Yeah, and then this is going to give you parts of your graph. So that's the window I'm going to use just because I have this limited space here. And then of course when you're doing that, you can choose your own window. And we're going to go ahead and check out our table. So I'm going to start at 0. It's your vertical asymptote. So you always put that on your chart. That's where you're always going to start because we want to see what's happening on either side. And if we want to see what's happening on either side, remember, we've been looking at what happens right next to it with the halves, like -1.5 and -2.5. And then at -1, I can see I'm at 4. Whoopsies. Okay, so at -1, I'm at 4. At 0, I'm at 1. 1, I'm at 4. 2, I'm at 8.5. Maybe I go to 4 where I'm at 19. Okay, and then, so if I'm going out to 10 on my graph, I'm going to have to go by 2's here. So 2, 4, 6, 8, 10. 2, 4, 6, 8, negative 10. And then I'm going to go by 10s on my y's because I do want to get up to that 30. And then in the negative part, I can see at negative 3, I'm at negative 44. At negative 4, I'm at negative 41. And I'm going by 2, so then maybe I want to start choosing those values. Okay, so I can go 10, 20, 30, 40, 50, 10, 20, 30, 40, negative 50. I have my y and my x. And then when I want to find the ones with decimals, I can just do my table start. So then I have 19 here, negative 59 there, so that'll be perfect because I went out to negative 60. Okay, so what we like to do is we like to set the boundaries. So we're going to do the asymptotes. So remember, I decided to go by 2. So my first asymptote is going to be at x equals negative 2. And then we're going to talk about the slant one. Because yesterday when we did this, we had a nice linear function. And when you have a linear function, where do you start when you're graphing? Nope. Y-intercept, which is, in this case it is negative 8. So I'm going by 10, so I would have to estimate negative 8. And then if I use my slope, I'd have to go up 6 over 1. Now when I'm going by 10s, that's going to be a little more difficult. So how else can I find points on this line? Yeah, do what? You can, but how would you, so, and then where would you go? So if you use your graphing calculator, where would you go to get your points? You go to your table, right? So whenever you need to find out where points are, just make a table. Because we already know 0, negative 8. If I'm going by 2's, can I just plug in 2? What's 6 times 2? 12. What's 12 minus 8? 4. So one of my points is going to be at 2, 4. So that's going by 10, so it would be about right there. Okay, then I can plug in 6 would be the next one. What's 36 minus 8? 2, 4, and then 6, so it would be at 28, so I'm almost at 30. And you could plug in 4 too. I was just skipping so we didn't have to do a bunch. And then 6 times 8 is 48. 48 minus 8. That's a nice one, right? So this is a straight line. So we're just connecting these points with dashes. All right, and then let's get some over here. So at negative 4, negative 24 minus 8. Okay, and then maybe we plug in negative 8. So negative 48 minus 8. Okay, so now we have our x on our chart. We know that we're going to have like some soft V shapes inside there, so that's what we're going to graph. When you have negative 6, 2, 4, negative 6, this is going to be really close to 50. That's my 41, really close there. And then I did negative 3, so remember, negative 3 is halfway in between there, so it's at 44. And then at negative 2.5, I'm at negative 59, so right here. So I have these 4 points. I'm going to connect this with a curve.
You have negative 5 above the negative 4 on your table?
Yes, you could find it in your table there. I didn't put it in, but you could put that other point in there. I did negative 6, yep. Just because we were going by 2s.
Yeah. I was looking at the other table for a second.
Oh, yeah. Yes. So this is for this. Okay, and then at negative 1.5, I'm at 19. And at negative 1, I'm at 4, so negative 1 is going to be about there. And this would be really close to the 20. At 0, I'm at 1. At 1, I'm at 4. Maybe a little bit lower. And then at 2, I'm at 8.5, so that's close to the 10. At 4, I'm at 19, so close to 20. At 6, I'm at 30.5. Okay, so then again, you're connecting this with your curve here. And then do you see how they follow along those asymptotes? Okay, and you need these points so you know like where your curve is. Okay? Okay, now for the last thing, is called the point of discontinuity, and this happens when something cancels out on the graph and it creates a hole. So we call this point discontinuity because there's going to be a hole in the graph. Okay, so it looks like a hole in the graph, and that is your main thing that you're going to be graphing here. Okay, so there's a hole in the graph, and the reason why there's a hole is because the function is undefined at this point. So this has to do with the cancellations that we talked about in 9.1 and 9.2. So if you have an original function that's undefined for a certain x value, your book just calls it x equals the value of a. So if it's undefined for x equals a value a, but when you simplify it, it is defined for that value x equals a, then that's where the hole occurs, at x equals a. Okay? A is any real number. So this is going to make better sense once I show you an example. Okay, so if you look at part B, what would x not be defined for in the original function for part B? For part B. For part B. Yeah, -2. I know. I just think that I want people with me. So this would be a time when you would define the original function. You find where it's undefined. And then if something simplifies, then it's going to create a hole. And so for example 3, you're going to see this cancellation. So in order to see it, you have to factor. So that's the first thing you're going to do. You are going to factor. So there's nothing to factor in the denominator. But in the numerator, you can split it up into x and x. What multiplies to -8 but adds to -2?
Plus 4. Or -4
plus 2. -4 plus 2. Okay, now, if this was 9.1 and 9.2, what would we be doing next? Yep, and that's called simplifying, so we're going to simplify that function. So when we simplify, we can cancel out the common factor. And then what would you be left with? Just x plus 2, right? Over 1, which is the same thing. So let's look at this function. What type of function is this? Linear. So we are going to graph the linear function, but there's a hole in this function. And that is going to be step 3. So before we can graph it, we have to find where that point of discontinuity is. So point of, and then I'm going to start abbreviating this so we don't have to write it out every time. Okay, so we know that the original function is not defined at what value? Yep. So since the denominator of the original function is x minus 4, x cannot equal 4. So the point of discontinuity, so I'm just going to call it the point of disc, is at x equals 4. And this is where the hole is going to occur. So before you set up your graph, you should find out what the point is. So if x is 4, okay, what is going to be your y value when x is 4? 6. You just plug it in, right? So if you plug in 4, 4 plus 2 is 6. So this is where the hole in the graph is. So when you're setting up your axis, just make sure that you can get to the 6 or wherever your point is. So here's my y, here's my x. And then whenever you're graphing, you start at what point?
Y-intercept.
Yeah, what's your y-intercept for that? 2. What's your slope? 1. Okay, so we're going to start at 2. If your slope is 1, you just do your rise over run, right? Up 1 over 1, up 1 over 1. And if you want to put the hole in your graph right away, you can. So this is 2, 3, 4, 5, 6. 1, 2, 3, 4. Okay, and then up 1 over 1, up 1 over 1. Okay, so then your graph is going to be a line with a hole in it at 4, 6. Okay, and that's all you have to do, and you're always going to do that when it says to find this point. Okay, so you're going to graph and you're going to find that point. Okay, there's no other asymptotes, there's none of that. It cancels and makes a linear function. Okay? I know. Okay, so I'm going to give you the rest of the time to work.